Over the first several slides, I'm going to ask you to just look and not write anything down. In the amount of time that we have, it's just going to be kind of a machine gun kind of a presentation where I'm going to be firing several things at you. But just to kind of lay a foundation, this is not what would be tested on. For instance, this guy right here. There's nothing. Hi. Did anybody see that? What did it look like? This one's been in the drawer for a while.
Oh no, it's like one of the thick ones.
I haven't seen it in the 2 hours that I've been in here. Hopefully somebody recognized it was yours during your hour and picked it up. I haven't seen it. I'll make sure I set it aside when everybody leaves. Okay. This guy, this is kind of cool too. Right at the beginning of a new century, in the year 1900, this German physicist, Max Planck, which of course I'm giving you the American pronunciation of his name. His name was Planck or something like that. I don't know how you would pronounce it in German. Who's got German class? Shaitan, you got German?
Right, but I don't know.
Oh, do you have French? Okay. But anyway, you saw in the reading about quantized energy. This guy was the first to make any suggestion at all about energy being quantized, about energy only having certain allowable values. And he did a lot of work with light waves. Bohr did too. Don't write any of this down. I will later on have you write this formula down with the variables defined, but that's in a later slide. This was a revolution in physics. It took quite a stretch of faith for people to buy into this. And then came Niels Bohr. And Niels Bohr just made people outright mad. I mean, Niels Bohr would be trying to lecture on what he thought electrons did, and people would get angry and they'd stand up and yell at him because they thought he was just blasphemous, because he was trying to suggest a form of physics that was not based on Isaac Newton. And I mean, everybody just bought into the laws of Newton as the way to describe how things work. For instance, with Newtonian physics, if you take a bowling ball and you just roll the bowling ball will just roll, and you could track any point in the bowling ball's motion. You could track a time interval, one instantaneous interval, any part of that bowling ball's motion you could watch and account for. But according to Niels Bohr, at the atomic level, you can have an electron. Let's say that the floor is the nucleus of an atom. You maybe have an electron here, and then an electron up here, and this electron can jump up to this energy level to be with this electron, so you can find the electron around here, but it's never in between the two. And people would get so angry. How can an electron go from here to here and not account for it in between? How does it get there? Well, Bohr said, well, I don't know. And even to this day, we believe that energy is quantized, but we still don't know how the electron can go from there to there, but never be in between. It doesn't stop in between, or we don't have any accounting for it being in between those two rings. Now this is simplified. We don't think that electrons just go in rings. It's a simplified view. But Niels Bohr, turned out, was only studying the element hydrogen. And for hydrogen, this is a fine example, because hydrogen only has one electron, just one. So we could conceive of it just being in rings and traveling around the nucleus in an orbital kind of a motion. Now what Bohr did, I want to show you this. It's worth just looking at quickly. I'm going to give you a pair of glasses. These are the diffraction gratings. You maybe, if you had Chem 1 here at Troy, you've used these before. These crazy things, they're only worth about $1. And man, do they give us plenty of entertainment. Try not to put your hand all over the lenses on this.
Puts these on. I don't see color. I just saw prints.
I'm glad I can help. That's all. Okay, I'm going to turn the lights off.
There's like 6.
Now, in the back of the room, I have this power supply. Niels Bohr was studying hydrogen. Listen now. Niels Bohr was not working with beakers and glassware and mixing hydrogen with stuff. He was taking hydrogen, he put it into a tube, a glass tube, and he ran a big voltage through it. That big voltage caused hydrogen atoms to split apart. Well, hydrogen molecules, H2 molecules, split into hydrogen atoms. And when they do that, the electrons will start jumping around from one energy level to another. Niels Bohr looked through a prism at the light that hydrogen gave off when he did that. And I want you to look at this. Don't look directly at the light. I mean, you can look at the light with your glasses on. But look over to the side, like where my hand is. Do you see a spectrum of light coming off of the hydrogen? Now, in that spectrum of light, you should see a few very bright bands. There's one that's teal, one that's red, and there's actually 2 purple ones, but one of them is really hard to see, the purple one. Like against the dark background of my shirt, can you see the spectrum over here? Yeah. These, now, I have to tell you, and I thought that I would just pull a pair of glasses out for my friends watching this online. All right, so if you're watching online, I'm going to take you right up close. I'm sorry, I'm standing in some of your way. But now, watching online, you can see these rainbows. Can I point to it? You got that rainbow coming off there. And then within the rainbow, there's these bright bands of light. There's that red one, that teal one. Bohr would have used something that was higher quality than $1 glasses. And let's see, I'm just going to keep this up, kind of aiming that direction because I'll be back there for a moment. Those bright bands of light were what gave Bohr the idea that they must correspond with the electrons jumping from one energy level to another. Bohr would not have seen that continuous spectrum. We just see the continuous spectrum because these don't filter the light out very well. So we get more waves of light than we should with this. However, with a good prism, you would only see those distinct bands, and it would be just darkness in between. If you look up at the board, that picture that I have in the lower right corner, that has hydrogen, and you can see that there's that teal band, there's the red band on the right, and then there's the, it's hard to see, there is a purple band, like underneath the D in hydrogen. Between kind of the Y and the D, there's a bright, not bright, it's not very bright, it's hard to see, but there's a band. All right, now I want you to also keep your glasses on for one more thing. One thing that's really cool about atoms and the way they behave is that every single element will give off its own distinct spectrum of light. I want you to take a look at this element. This is neon. And even if you've seen neon before, it's such a great effect. Notice how different the spectrum of neon is compared to the spectrum of hydrogen. You can see that the spectrum is dominated on the red side. Yep, so you can see even on the TV or the computer, you have these bright lines that are coming off of the neon, like over even with the sinks and the faucets. There's a kind of a yellow one and then a whole bunch of red lines. That would be the spectrum of neon. So that's when we talk about neon lights, that's a neon light. All right, go ahead and take your glasses off. Just put them on your desk. I'll get them in a few minutes. Not ready to give them up yet? Astronomers use this kind of science to determine what elements are in stars. They can tell how old stars are. I left the neon on. They can tell how old stars are from what elements are inside of them. As soon as the star starts producing iron, the astronomers know that the star is going to start dying off. Okay, well, I'm just going to ignore that for now. This also, I don't want you to write down. You saw this equation in the reading assignment. This is the equation that Niels Bohr used to calculate how much energy the hydrogen electron had. And it was perfect. You can reflect every single energy level of hydrogen with this equation. The problem is, this equation is only good for the element hydrogen. It doesn't describe electrons in any other element. And Bohr couldn't come up with a different equation to represent the electrons in helium or any other element. He just had this one equation for hydrogen. So Bohr, he didn't quite achieve what he hoped to achieve because he could only describe one element. Now this is just another picture of what Bohr thought the electrons would do in hydrogen. When you have a hydrogen atom whose electron is as close to the nucleus as it can get, we call that the ground state. Even Bohr would have called it the ground state. When an atom gains energy and its electrons jump up to a higher energy level, they call that an excited state. The electron has become excited. And this would show an excited electron in the second energy level. If this is the first energy level, that would be considered the ground state for hydrogen. This electron is on the second. When the electron returns back down to the ground state, which, by the way, is not stable at all up there, so immediately it's going to fall back down to the ground state, it releases energy. And that energy is a very specific frequency of light. And so that was what Bohr was determining was happening with the bands of light that he saw. He was able to calculate, based on the energy of the light, what the energy of these levels were. Now, here's the part that I do want you to write down. This is the first thing that would be appropriate to write down. These two equations. E equals h times nu. This thing right here, I know with this font in this chapter, this looks like a V. It looks just like a V. But it's not. It's a nu. It's a Greek letter for N. So energy of light is the E. It's equal to Planck's constant, h, it's defined over there, times the frequency of light. Nu represents the frequency. And then we have a second equation right underneath it. C is the speed of light. You've heard of E equals mc squared. That C is the speed of light with Einstein's equation. C equals, this thing right here is a Greek letter, lambda, it's a Greek letter L, times nu. What this thing shows is the relationship between, lambda is the wavelength of light. The wavelength times the frequency equals a constant. The speed of light is a constant, 3 times 10 to the 8th power. These two equations are, they're the foundational things for light waves. We have to know, we have to be able to calculate the energy of light. This top equation was what Bohr was using. He would be able to determine the energy of light and figure out how much energy the electrons have as they jump from one level to another. But this one is equally important. C equals wavelength times frequency. Wavelength times frequency, when they're multiplied together, it equals a constant. That tells us that wavelength is inversely related to frequency. If they multiply together to give a constant, that means if the wavelength goes high, the frequency has to go low in order for them to multiply and give the same number. So down here, I think it would be right to write, or correct to write all those things. What H is, the value of H and the value of C, the units for it. Frequency is kind of an unusual measured value. Its unit is weird. The unit on frequency is hertz, which, okay, it's a hertz, but what does a hertz mean? Really, frequency is measured in how many times waves are happening per second. How many waves happen per second? That's what frequency is. Over here I have a board. I've got a board.